you. It's still a pleasure to be here. Yeah. I made a lot of promises of what I was going to do later yesterday, and I'm not going to get to it all. I rearranged the order in which I'm going to talk about things here. And so I want to start off, just to make sure I absolutely get to it, is sort of the heart of the philosophy of semi-symbolic groups and coronal groups and automatic groups is the fact that you study normal forms. So it's the geometry and complexity of a very classical notion in group theory of normal forms in discrete groups. So what is a normal form? It's just this kind of a preferred way of writing elements of a group. So that's all it is. So throughout, so you've got a finitely generated group. Okay, so A is just some finite set. Now, you normally then think of the free group on A. What does that mean? It means the free group on A maps. Implicitly, we all think of it like this. You think of inside gamma, you've got some finite set of elements that generate the whole group, right? But that's actually not what you should think. What you should think is there's a map from the free group on the A, from set A to gamma, right? The sends of two particular maps. And in fact, when you think about normal forms, you don't want to think of the free group. What you actually want to think of is the free monoid Now, so that's the free monoid on A, and then you have a formal set of inverses. So for each A here, you invent a symbol called A inverse. Okay, so to say that A generates the group means you have a map from the free monoid to A, and if you're going to do this sort of business, you better require that that's just a formality. Okay, now, but why do I want to put it a free monoid rather than free group? Because, see, what is the free monoid? So the free monoid is really just the words, finite words in the alphabet. And so the point is you don't freely reduce words. Okay, so e.g. Something like A inverse, A inverse, A inverse is a sensible element of the free monoid. Whereas it's not a sensible element of the free group. Okay, so it's really words, so it's not the free group, it's the free monoid thing. So this is just words in the generators, and then obviously mu is just an interpretation element. Henry told me to do this, but I have a good reason for doing it here. I apologize. And so a normal form, definition, a normal form, and then you give it an alternative name here. In general, it's a bad idea to give existing objects a new name, but it's because it's a change of perspective. There's a section. Let's go the other way. It's a section of mu. Okay, so just by which I mean, that if you go this way and then that way, i.e., that sigma gamma mu of sigma gamma. So what is it? So 6 thus sigma of gamma is a choice. Fixed choice, which you hope to be making in some intelligent way of word and generators representing, that is to say, equal in gamma. Okay? That's all a normal form is. It's just some choice of word the generators. Okay, so that's a very classical thing. So what's the new word I want to put in there? And he keeps teasing about how old I am, it was new in the 90s. Combing. Okay, so that's the new word. It's just a new word, and it just exactly means normal form. Now why bother introducing a new word? Well, because there's a change in perspective. Okay, so the perspective, so let's go first in this way. So all of this Palmer stuff I learned from Bill first. Let's go first. So what you want to think of this, you see, you want to think of the free monoid as sitting aside paths, discrete paths in gamma. So paths, discrete paths in gamma. So what is this? This is just all maps from the integers to gamma, so that D is eventually constant. In fact, you can normalize it here, so that the distance between P of T and P of T plus 1 in the group is never more than 1. Because, so you think gamma or I think of it as discrete paths, so I don't really want to think of a Cayley graph. You can think of this as continuous paths in the Cayley graph, if you like. Say you're doing z squared, right? So you give me a word, say x squared, y, x inverse, y inverse. Okay, so we all know you can think of that. Oh, sorry, I want these paths to start to grow. Yeah, so you give me a word, and that obviously describes a path in the Cayley graph. Okay, x, x, y, x inverse, y inverse. Okay? So words are paths in the Cayley graph. You just restrict to integer times when you're visiting the vertices. So this is the change of perspective. Right? So you want to think of words, the elements of the free monoid, as discrete paths. Now when you think of them as discrete paths, you've now got a geometric object, right? You've got a family of paths, right? So thus, a coning is a choice of preferred path called sigma gamma from the identity of the gamma to gamma and gamma, and that's called gamma and gamma. And it's a path that's got at most unit speed. Okay? That's how you should think of that. Now when you think of it like that, then it sort of naturally, so what's the point of the change of perspective? It naturally begs the question, well, what's the geometry of a good normal form? Right? So instead of just asking how simple algebraically a normal form is, now it's natural to ask, so we have two problems. So natural. Now, from this point of view, so natural is only natural after you've got to change this perspective in this way. Natural questions. One, what nice geometry of the set of paths? Now I call this L sigma. Might imply interesting properties of the group. Okay. So you try and articulate, say, if a group admits a normal form of a particularly nice sort, then the group will have the following nice properties. And then, of course, we'll try and prove that the groups you care about have normal forms with that nice sort. Okay? So, first of all, we ask about geometry. But we haven't forgotten algebra entirely, and it is still a set of words. Okay? The second is how nice might can be made language. I don't know which of these colours can you see. This is for Northern Ireland beating Germany tonight. Green. Language. You see that? I'm not sure you're going to see how the people Germany. Can we make a language? This is, after all, No, it is a language. It's a set of words. Okay, so remind you that just the words in the alphabet. So it's a perfectly reasonable linguistic question. You've got a language, a set of words. How easy can you make that? How kind of linguistically simple might you make that? How nice can you make that? And what will this tell us about the group? Right? So everyone agree those two natural questions, that there could be this nice, there's interesting answers. Okay? So that's sort of the basic context of what I'm doing. This whole philosophy of automatic and semi-hyperbolic groups. Okay? So this is what context for automatic semi-hyperbolic and what will naturally be called homable and other variations groups. Okay, and we'll think about what natural geometries are. Now I'm going to motivate the geometry, so shortly what we would do is we would go from hyperbolic groups and cat zero groups, and we would go from there to interesting, we can use those to motivate nice geometry. Okay? So that's going to postpone that for a minute, and I'm going to start talking about the other part of this, the language. Okay, so we've got a subsection on languages. So, languages. And this is something I got very taken with 20 years ago. Okay? If you've never read Noam Chomsky's thesis, I highly recommend it. Right? It's a model of the clarity of human thought and writing, and it also sort of takes natural ideas like how complicated the language is, and just makes it very precise. And this is something that's of interest to computer scientists, of course. And there's a hierarchy, the Chomsky hierarchy of natural. So he was interested in natural language. I'm not interested in natural language. I'm interested in mathematical languages. But there's a hierarchy, and some of that hierarchy goes like this. Okay, so these are increasingly complicated classes of languages. Okay? There's regular languages. Those sit inside a larger class called context-free languages. Now, there's some other things you can put here, but I'm interested in something called the index languages. Introduced later by Aho. Indexed language, so that word is index languages. And these are all subsets of a large class that's widely studied by linguists and computer scientists, the context-sensitive languages. I'm not going to talk about context-sensitive languages. I think I'm going to talk a little bit about context-free, but I'm going to talk about how these two have particular interest from the point of view of geometry. Okay? Now, I'm going to try and define these quickly. I could try and avoid it, but I think I've just got to do it. So, how do you define these? So, there are definitions in terms of formal grammar. Okay? So, formal, what's called generative grammar. I'll just give you a little example of that. It's you have things called terminals and non-terminals and a start state, and that's a start state where you think, oh, I'm going to build a sentence, S. Okay? And then X goes to something called X and Y, and then X is allowed to go to X, or you can just go to X, Y is allowed to go to Y, or it just goes to Y. That's an example of the grammar. What language does this generate for you? This is a grammar that generates the language X to the N, Y to the N. You have things called productions, right? So you start with S, and then you go to XX, and then maybe you spit out a few X's, and this is a whole bunch of productions here, and that spits out a few Y's, and then eventually they decide to give up, and the X just disappears, and maybe the y will go up as well. Okay, and then you get x to the fourth way. Okay. So you can sort of imagine machines just randomly plugging away, choosing which one of these operations to do. What are all the words this machine will spit out? It's exactly that language. That's an example of something called a regular grammar. Okay? And there are more complicated versions of that that define context-free and indexed languages. Okay? So that's all I'm going to say about grammar. But in a minute, I'm going to tell you about some geometric theorems about languages that rise from geometry that have certain complexity, and actually constructing suitable grammars is the way that a lot of this goes. Okay? So that's a very real way of generating interesting languages in geometry. So that's one way you can define them. There's an alternative definition in terms of automata. Simple idealized machines, and that's what I'm going to give you. Okay? And corresponding to these language classes, there's something called a fairly stupid automaton, more politely called a finite state automaton. And this you should really think of as being built by Neanderthals. Then there's these correspond to something called a pushdown automata. And there's something which is to do with that or over there. You should think of these as non-deterministic machines, but I'm not going to dwell on that. From today's point of view, that's just a detail. And these correspond to something called nested stack automata. And rather than spend a lot of time on definitions, what I'm going to do is give you honest examples to show you what's going on. And as I'm describing these examples, I will not real definition. Okay? So, first let's do finite state automata. These are the most important ones from our point of view. A finite state automaton. So let me give you examples. So finite state automata. So it's just a machine. So you should think of it as a directed graph. So you can think of it as a certain type of Turing machine with a tape being fed in and so on. But you can think of it as a directed graph with the start state, S0, the element of the vertices. And because we're doing computer science, the vertices are called states. And then the states are divided into yes states and no states. Okay? So you start somewhere, that's 0, and then you've got a bunch of other states which you think of as fat vertices. Okay? And some of them are yes, some of them are no. And between these, so from each state, you have arrows, like directed arrows going out and coming in. And what you're supposed to have, so you have an alphabet, an alphabet, and that's the alphabet of the words that sit on the tape that's being fed in. And for all states, so there's vertices V prime, you have an arrow going from, for all states V, and for all A and A, you have an arrow going from A to some other state. Okay, some other state. There's some arrow going out. And that tells you where to go. So you think of this as, so think of this, I always imagine myself standing in this machine, somebody up there is reading the tape, they're shouting out the letters they read on the tape, they say A, and I look for the arrow that's there from A going out of my vertex, and I walk along the edges to the next vertex. That's all it is. Okay? It's a very simple machine. Okay. Normally, you don't bother drawing arrows if they go to fail states. A fail state is one where you get stuck and the answer is no. They usually don't bother drawing those. It's a detail. Let me draw you an example. So here's an example. If I take the alphabet to be just X and Y, okay, so coming out of my start state, I have an X, I have a Y, I have a state I call capital X, and stay there. If I keep reading y's, I stay here. If after I've read a bunch of x's, I read a y, I go here. And everything else fails. Okay, so from here, if I read an x, I go to fail state. Okay. And these are both yes states. So this is a yes state, this is a yes state, this is a no state. And once you're there, life is over. Right, what language is accepted by this? When you read in the tape, if you read x's, you go here, you keep reading x's, you're happy. Then you start reading y's, you can carry on reading y's, but if you ever read an x, you fail. Okay? So this is exactly the accepted language. When the machine says yes, you're good, you're in, is exactly this language we had a minute ago. So x to the n, y to the n. So that's a regular language. Okay? That's accepted by that particular finite state.
What happens if you try to read empty word?
The empty word, I just sit down and have a cup of tea. Just stay where you are. Yeah. You can put the empty word in. You can stay. No, you can decide whether the initial state is an accept or reject. That's up to you. Yeah. No. Sorry, was that your question? Yeah, the initial state can be, you decide whether you want the empty language. Normally put the empty word in. But that doesn't happen sometimes. Oh, well, it depends whether you think 0 is a natural number. I'll leave it up to you. Yeah. All right, that's, if you think 0 is a natural number, you say the initial state and accept state. If you don't mistake it. I think 0 is a natural number. Okay, so that's the yes state. Thank you. Right, now let's have a more interesting automaton. Okay? Yesterday I told you Hammond's theorem that the language of geodesics, so if gamma is hyperbolic, then the language of geodesic words is regular. I'd tell you what that means, right? I just told you. That literally, I read this, okay? There's a finite state automaton. You give it a word, and the generators will tell you whether that's a geodesic word. So in other words, what's a geodesic word? Right, going from W to gamma. Okay, so W equals gamma. If W is equal to the distance, if the length of W is exactly the distance from gamma, then that's a geodesic. Okay? Just the naive meaning of geodesic. The claim is that the hyperbolic groups you see pictures of, you think they're fantastically complicated. But it comes down to all these results I was saying yesterday about local recognition of geodesics. Okay? You can locally recognize geodesics. And so in fact, defining a fairly stupid automaton, a finite state automaton, can recognize whether a word in the generated hyperbolic group is geodesic. So let me tell you what's the machine. So what is the finite state automaton? Now, so the vertices, so M geod, that accepts, recognizes this language. Okay. So the vertices, or states, of this machine are the cone types. Okay, so what's a cone type? The cone type of an element gamma is the set of words u, okay, set of words, so that the distance in gamma from 1 to gamma u is equal to the distance from 1 to gamma plus the length of u. In other words, when you're standing at gamma and you're back to the identity and you look out towards infinity, you ask yourself, suppose I've come from the identity along a geodesic, and I want to continue along a geodesic. What are all the possible ways of continuing? Right? So you come from the identity, on a long walk, train to Cambridge, you arrive at gamma, and you want to know, going forwards, what it's called cone type, what are all the words u that I might do next, so that I'm proceeding maximally quickly away from the identity and going along with geodesic. That's the cone type. And the theorem is, it's not hard, it's like those stability talks I was talking about yesterday. So Camden's I guess it's a lemma, it's a key lemma, Camden's lemma, is that if gamma is hyperbolic, implies that there exists only finitely many cone types. So why would you believe that? Sorry, I'm shadow here, aren't I? Okay, so that is, so no matter, the claim is, wherever you stand in the group, you look out to infinity, and you look at all the words that take you away from the identity. So the claim is, forget what's behind you, the view you see looking to infinity, there's only finitely many possibilities for that view. Okay, the extension of the light rays, if you like, going to infinity through you from the identity. And the key observation is